Welcome to all of you. Very good evening to all those attending this talk. And we thank Dr. Kazi Rajibul Islam for agreeing to give Quantalks number 6. The title of his talk is Programmable Quantum Simulations with Laser-Cooled Trapped Ions. He's from the Institute for Quantum Computing and Department of Physics and Astronomy from the University of Waterloo. Thank you, Rajibul, for accepting to give a talk on this. I can see there's some exciting work that you're doing with laser cooling of trapped ions. Now, I request my colleague Basudev to introduce the speaker.
Hi. Can you hear me for a start? Yeah, I think.
Yes.
Yeah. Okay. So this is Rajibul. He's a good friend of mine. Actually, I'll explain to you why. But in brief, his CV looks like he did his undergraduate at Jadavpur University, and from there he went to DIFR. He did his MS with Mustansir Burma, I believe. So there in MS, I think he graduated in 2005, and then he went to University of Maryland. He was there for a substantial amount of time there, but in Chris Monroe's lab where he did his ion trapping. So that's where I met him. So he was just next door to me. So yeah. After that, he went on to MIT and Harvard, whichever order it is. Vladan Buletik's lab and somebody else in Harvard, I think. So Marcus Greiner. Yeah, Marcus Greiner. And he has published a lot of good stuff, nature, science, all kinds of things. So after that, he got a job at the Perimeter Institute in Canada, the University of Waterloo. And so he has been there for, I think, past 3 years. And he has been winning all kinds of awards from the Canadian government and all kinds of places. Even the university, he got an award. So okay, so I would pass the baton on to Rajibul to tell us what he has been doing and the exciting stuff he is involved in, and those 8 ions he has been describing in that picture. So he'll tell us about that. Okay, over to Rajibul.
Thank you so much, Professor Rao and Vasudha. Thanks for inviting me, and it's so good to see my good old friend after a long time. So thanks for the introduction. I work at University of Waterloo. So Institute for Quantum Computing is essentially an interdepartmental center at University of Waterloo, and I also have affiliation with the Perimeter Institute. They are nearby, but they are distinct entities. So I'm going to talk about programmable quantum simulations with laser-cooled trapped ions. And first, this image that you are seeing on the screen, let me tell a little bit about it. Essentially, what you are seeing, each blob of light is a single atom. It's a single atomic ion, and they're separated by a few microns. These ions have been cooled to very low temperatures. They are about a millikelvin, and we use laser cooling to cool those. So it takes only a few seconds to cool these ions from a very hot temperature oven, like few hundred degrees Celsius, all the way down to a millikelvin, just a few seconds with lasers. And this whole thing is inside an ultra high vacuum chamber. So this video shows how you can sequentially trap 1, 2, 3, 4, 5, and so on number of ions. These are Ytterbium ions here. So the goal for our research, and I'll try to give a flavor of that in this talk, is to use these ions for quantum information processing, and in particular quantum simulation. So these days there are, I'm sure you have been hearing a lot of buzz around quantum computers. There are governments funding, academia, industry, even quantum computing companies going public in stock exchange. And the difference between a quantum simulator and a quantum computer is that a quantum simulator is a special kind of quantum computer. You can say it's a custom purpose built quantum computer that can solve few types of problems, not necessarily any quantum algorithm that you can think of. So in this talk, I'll be focusing on simulations for many-body quantum physics. So quantum many-body systems. But for trapped ion architecture, you can actually use the same machine for running quantum algorithms, other kinds of quantum algorithms too. So with that introduction, let me just spend a minute talking about the Institute IQC. You see top right corner, this is the building where we are. It looks nice, but also the building has lots of nice features like low vibrations and all, which makes these kind of experiments possible. There are 32 research groups, roughly 19 experiments and 13 theory, all devoted to various aspects of quantum information science, work with various platforms like trapped ions, NMR, even molecules now, quantum optics, superconducting. IQC also runs its own programs jointly with other departments, like a master's in quantum information and PhD in quantum information. And I'd like to advertise that we have a very vibrant and competitive undergraduate summer research program called USKIP. The students who are selected, they normally in pre-pandemic time and hopefully post-pandemic as well, they're brought to IQC. They spend a few weeks attending the summer program, and then they can stay on with one or more faculty members doing some summer research, and all the expenses are covered by IQC. So please advertise this to your students and encourage them to apply for undergraduates. My group started in 2017, so I've been there for almost four plus years. And of course, this is a picture in the pre-pandemic times when we were still allowed to socialize and go outside. You're seeing the Niagara River in the background. We are very close to the Niagara waterfalls. And the work that I'm going to talk about, most of that work was done by dedicated group of students, my graduate students and postdocs. And also we get lots of very talented undergraduates in our labs. And thanks to the funding agencies always. So this is what we do now, virtual meetings on Teams. Okay, before I start talking about quantum simulation, I just want to clarify for the audience that I have split my talk into smaller sections, each sections with a few slides on one theme. And I would very much appreciate if you engage with me, interact after every section. I will pause and I will invite questions. So please ask anything. It's fun to be interacting and not just talk to my computer for a whole hour. So a few words about quantum simulation. The basic premise is that if you want to understand properties of a quantum many-body system, that's in general very hard, especially if you are studying quantum dynamics, any dynamical phenomena, because in general, if you take a quantum state, it has entanglement, and entanglement are non-classical correlations, which by definition, in general, cannot be captured by simpler classical methods. So since you have an exponentially growing Hilbert space, for example, if you have n 2-qubit or spin-half systems, you have 2 to the n as the Hilbert space grows, with n being the number of qubits, or two-level systems or spin-half. Dealing with quantum many-body system becomes hard on computers. So in 1982, Feynman was thinking about that, and he asked this question: can physics be simulated by a universal computer? And when he said physics, he meant physics with its quantum mechanics laws. And he was thinking about this exponential growth of the Hilbert space. But he suggested, like many things that Feynman suggested, nano and plenty of room in the bottom and many other ideas, he suggested, why not build a computer out of quantum mechanical elements? So instead of our transistors using, we use the transistors as bits, 0 and 1, 0 or 1, why don't we replace those transistors with quantum mechanical elements that natively follow laws of quantum mechanics? And as a result, when we are trying to solve a quantum problem, we don't have to encode the laws of quantum mechanics into our algorithm, because the processor itself is quantum mechanical in nature. So that was his idea. It was made concrete later on by many researchers, and then over the last couple of decades, there have been an exponential growth in experiments. We have now better quality lasers. The laser cooling techniques are mature. There are various atomic systems. So, and also non-atomic systems. I'll show some pictures here. But then, so we are beginning to build small scale quantum computers. These are noisy. Often the term that's used is NISQ, noisy intermediate scale quantum devices. And as I mentioned in the beginning, quantum simulator is just a restricted class of quantum computer. So what kind of problem are we talking about? Let's say we have a macroscopic phenomena, for example, a high temperature superconductor, or inside particle colliders, you have this quark-gluon plasma that happens at very high energy. And we would like to come up with a minimal description, microscopic description of these systems, a minimal model between quantum degrees of freedom that can explain some of these macroscopic properties that we can observe in an experiment, in a macroscopic experiment. So this is in general a hard problem, because in a real material, there are so many different interactions going on. So what is the specific interaction that's responsible for one particular macroscopic property that we are measuring? This is a hard problem, and this possibly a quantum simulator can help. Exactly what these simulators are useful for, that is itself a field of research. But over the last many years, there have been several problems that were proposed for applications for a quantum simulator. For example, understanding chemical reactions, because that is also a many-body physics. A good application could be understanding nitrogen fixation, which leads to making better quality fertilizers, and it's a huge aspect of our life. Phase diagram of many-body Hamiltonians, and eventually, if we understand the phase diagram of complicated Hamiltonians, perhaps in the long run, we would be able to understand how to make new materials. More recently, people realized that you can use these quantum simulators to understand problems in high energy physics, like dynamics in quantum chromodynamics, QCD, which is in general very hard with any other method. And then, as I mentioned, predicting new materials, battery, and there are many applications. So any place where we have to deal with many-body quantum systems that's hard to simulate, potentially quantum simulator, once it's scaled up in the next years and decades, would be useful. So I want to give one example how a quantum simulator would work. So let's consider a classical simulation. Okay, so I have a Hamiltonian, and this is the transverse Ising model. So X means Pauli spin operator in X. So this means let's say you have a spin half system, so sigma X or Sx. So you have a Hamiltonian where the spins are interacting along X direction. This is the Ising coupling, summed over the whole. Spin could be nearest neighbor interaction, could be fully connected, whatever. So it's summed over that. And then let's say you have a magnetic field along a transverse direction. So this is a very favorite model of statistical physicists. And this shows lots of interesting features like quantum phase transitions at 0 temperature. If you want to understand, let's say, the evolution of a particular quantum state under this Hamiltonian, how do you do it? On a normal computer, you would first encode the initial quantum state in classical registers or bits. But remember, we are talking about a quantum many-body system. Therefore, the Hilbert space is 2 to the n dimension. So to write down a classical state of an n-body system, you need a memory, 2 to the n memory, and each one you need a few bits to encode the probability amplitude. So it's an exponential memory requirement. And then you turn on the Hamiltonian, meaning now on your code, computer code, you're solving, in general, Schrodinger's time evolution, or at least evolution for a density matrix. Now, of course, you can do a lot of simplification by assuming simpler structure of your initial state and various approximation methods like matrix product states and all. And finally, when you have the time evolved state or density matrix, you will compute probabilities, Born's rule, or however way you can compute probabilities, and the answer. But of course, you see that there's this exponential scaling. So if you're talking about 10 qubits, 2 to the 10 is about 1 kilo, so 1,000. By the time you're 2 to the 20, now we're talking about 10 to the 6. 2 to the 30, we're talking about 10 to the 9. So clearly, if you are dealing with a general quantum system of 30, 40, 50 qubits, you normally don't have enough memory on your classical processors to deal with this. How would you solve the exact same problem on a quantum simulator? So the idea is you find a quantum system for which you don't have to use the quantum resources. And that could be these ions that I was showing around. So this is a picture of, I think, 10 ions in our trap, which you can trap inside this ultra-high vacuum, as I mentioned. Now, each ion has various energy levels, and you can pick 2 that you feel comfortable working with using the 2 experimental tools you have. And you encode means down and up, or 0 or 1, depending on whether you are speaking the condensed matter physicist language or the quantum computing language. So label, let's say this one, the lowest excited state in the hyperfine manifold for ytterbium ion has been down, and the other one has been up. But now you have chosen a system which is quantum mechanical in nature, and therefore, in some sense, you are getting the quantum evolution for free. The system does it for you, it's native. You need to make sure that you have enough experimental control to be able to simulate the Hamiltonian that you think you're simulating. But otherwise, you don't have to do anything on the time evolution. And finally, you do a measurement. Now, in atomic systems, what we can do, we can shine precisely tuned lasers onto these atoms such that one of these 2 states will fluoresce light, will absorb that laser and then emit a bunch of photons, which we can then image, and the other state will not. And therefore, you shine that light and you do a projective measurement very quickly, like within hundreds of nanoseconds. And then you can read out the state. For example, this is one particular state from a simulation with 10 ions. And this particular state was spin up, down, like a nail state, antiferromagnetic order. But this is only one projection. And then, of course, you repeat the experiment under identical conditions many, many times to build up statistics and probability. And then you know the answer, right? So this is the distinction between a classical and a quantum. And in a nutshell, you don't need to encode, you don't need to program the time evolution because you are using the real quantum system. So there are a couple of different ways named as analog quantum simulation and digital quantum simulation through which this simulation can work. You can simulate the Hamiltonian, you can experimentally create the Hamiltonian and just keep the Hamiltonian on or slowly change in time and let the system evolve. This is called the analog simulation. Then essentially your experimental Hamiltonian is the same as the Hamiltonian that you want to study, right? Then that's an analog Hamiltonian. The other approach is called the digital quantum simulation, where let's say you want to study time evolution under a Hamiltonian, which is very non-trivial, and you cannot generate that Hamiltonian using your laser beams and all. I'll talk a little bit about how you generate a Hamiltonian using laser beams. So in that case, what you can do, you can break down the unitary evolution into smaller, simpler local Hamiltonians, right? This is the and then you repeat that with many cycles, and this is how it's represented. So each line represents one spin half object or one qubit, and then these circles, these rectangles represent quantum operations, which is time evolution under a simpler Hamiltonian for a finite amount of time, right? These are called quantum gates. So you can do single qubit quantum gate and 2 qubit quantum gates, and you can put them together into simulating the Hamiltonian. This is the digital Hamiltonian, digital simulation. And there is something in between which has not been explored very well. We started looking into it and several other groups recently, where you do a simulation part with an analog fine-tuned system, but then modify that with digital gates to make use of the best of the both worlds, essentially. There are various platforms, hardware platforms, and I'll be talking about trapped ions. There are neutral atoms, bosons, and fermions in optical potentials, superconducting circuits, Rydberg atoms, now even molecules, photonic networks, solid-state defect centers, and some other systems that you can use for quantum simulation. Each system has its strengths and weaknesses. So we'll be focusing on the trapped ion. So with that, let me pause and see if there are questions on the basic idea for quantum simulation.
Rajibul, I have a short question.
Please.
In these ion traps, you always have one-dimensional arrangement. What are the major difficulties in going to, for example, a cubic or a planar arrangement?
Yeah, so that's a great observation. Traditionally, we like to work with one-dimensional ion traps, and that's mostly the difficulties have to do with how you construct the ion trapping potential. So these are radio frequency ion traps. And I'll actually have a couple of pictures to elaborate in a few slides. But basically, it has to do with the potential. Let me stop there, and then I'll show you some pictures in a few slides. Having said that, I'll make two other quick comments. Number one, there are new experiments that people are building where you actually work with two-dimensional ion traps. There are several groups that started working on those. You also have another kind of ion trap known as penning trap. So these are radio frequency traps that I'll be talking about, called Paul traps. But there's another kind of ion trap called penning trap, where you naturally get a large two-dimensional ion crystal. There are some challenges working with penning traps. For example, the whole crystal always rotates because you are relying on the Lorentz force to trap those ions in one dimension. So, but people also use the penning trap. You hit in a large 2D crystal. And finally, as I will show in my talk, even in this RF trap, Paul trap, the ions are one-dimensional. A beautiful property of this trapped ion system is that the spin-spin interaction is long range. And in principle, if you have enough control knob, you can control pretty much every bond programmatically. So you can synthesize, if you wish, an arbitrary lattice from this one-dimensional system by programming the interaction between spins here. That is very powerful for quantum simulation. I will show that later on.
Thank you.
Rajibul, so in terms of what you have shown here, natural atoms, photonic networks, Emergent diamond, from the technology perspective, which one of these you think is more viable?
So, of course, I'm a little biased for ions, right? I work with ions, but I would say they have different strengths and weaknesses, right? And so if you are trying to solve a problem which is very close to the natural property of one of these systems, I would say use that, right? So let's say you want to understand how many fermions interact with each other. It's a hard problem. So if you can find a model system where you don't have to encode fermionic nature, but get a fermion, right? and then put it in some kind of optical potential so that they are interacting, and you have all of your phase buck resonance and all these controls to play with the interaction, I would say that would be better. However, if you're talking about fully programmable quantum simulation, so in the same hardware, you want to study 2D physics, 3D physics, 1D physics, you want to study boson, fermion, then you need more than these emulators where your system has a lot of property. And I would say definitely trapped ion is one of the leaders there, simply because trapped ion is also a candidate for quantum computing, meaning you can do high quality quantum gates. So even if you don't have a fermion in your quantum simulator, but you want to solve fermions, you can do all of these transformations mathematically from fermion onto spin degrees of freedom, and then run that spin circuit on this trapped ion system, and then you simulate fermion. Whereas if you have real fermions, like a neutral atom fermions in optical lattice, that's great for simulating fermion, but that may not be great for simulating another different kinds of system. So that's why I draw the distinction between these systems. Yeah. All right.
So may I ask a question?
Yeah, please go ahead. Yeah.
Yes. So I was just so when we talk about this manipulating spins and other quantum mechanical systems, I'm sorry. So it is like our intuition is the system will definitely work faster or more efficiently than a classical system. But when we say that, okay, we have to think about or do research on where or in which cases the quantum mechanical computers will be more efficient, why we are saying that in some cases the classical computers or classical bits will be more efficient? Is there any example or any specific reason?
Yeah, this is a good question and a matter of debate quite a bit. I would say to make a definite statement that a quantum processor definitely gives you a speed up over the best classical processor in general, not for simulation, but in general for quantum algorithms. To make a definite statement is very hard, right? So let's say you come up with some quantum protocol and compare with classical protocol, and then you send that paper out for review, and reviewer always can come back, well, because your classical protocol is not the smartest one. I can come up with a better classical algorithm or a better programming, better coding. So what you are pointing to is this kind of burning question of quantum advantage or quantum supremacy, right? And there are only a few known examples where quantum evolution truly gives an advantage compared to classical. However, when it comes to quantum simulation, it is true that simulating the dynamics of a many-body system is always classically hard, unless you can approximate the state as a state which doesn't have too much entanglement, which is true in some cases, but not always. So this is one example where we definitely believe that a quantum machine will help you, but then mathematically proving quantum advantage is always challenging. Okay, so yeah, unless there are another quick question, I would move on.
Hello, Professor. Which type of trap is more suitable in the case of this processing, especially simulation process you have considered? RF trap or any other quarter pole trap? And what is the advantage in terms of MOT?
So we don't use MOT. Neutral atoms use typically MOTs. We use RF Hall traps. That's traditionally used because you have static crystal, but then also there is the penning trap, which is the other kind of crystal, other kind of ion trap that's used. I'll show you some pictures here since we are talking about ion trapping. Yeah, I don't have too much time to go into detail of ion trapping, but this is quite basic physics, so I thought I'll talk about it. If you want to trap a charged particle in space, what you need is force fields that all point towards that that point in space. But you can't do that because you have to satisfy Gauss's law in free space, or also known as Earnshaw's theorem. But Wolfgang Paul, I think in 50s maybe, came up with the idea of using a time-dependent field, so radio frequency field. So here's the idea. Consider this system. You have 4 rod electrodes and then 2 needles, and then you apply oscillating voltages on the diagonals, and then static voltages on the edges, right? So then the static positive potential will create a confinement for the positively charged ion near the center along this direction, Z direction. But then in X and Y, because the potential is oscillating, at every time step, you're going to get a confining direction and an anti-confining direction. But the trick here is this. If your potential is oscillating fast enough, by the time the ion tries to fall from the anti-confining direction, it changes sign. And then it becomes a wall again. So it pushes the ion back. And as a result, if this oscillation is happening at a much faster time scale than the, let's say, the trap frequency, the motional time scale for the particle, then it's trapped there. It still executes a little bit of small oscillations at the frequency of the confining potential. This is called the micromotion. But you can trap an ion, right? So to answer Professor Bhaskaran's question of why typically we do a one-dimensional ion chain, here's the reason. So take this trap, for example, very popular trap called 4-rod ion trap, Paul trap. By symmetry, you can see that the radio frequency has a line of 0 called radio frequency null along the Z direction, because the rods are just by cylindrical symmetry. And so if you place these chains of ions on that radio frequency null, they experience the time averaged potential, but they don't actually oscillate with the potential frequency. So they are stationary or very close to stationary. So that's why we like to put our ions on the radio frequency null and work with them. Does that make sense, Professor Bhaskaran?
Sure. Yeah, beautiful. I agree.
Okay. You can actually build an ion trap in your lab, even undergrad lab. So my undergrads built this. It's so much fun. You take 4 razor blades and they gold coated it because they didn't want it to oxidize, but you don't need it, just some metallic blades. And then take 2 banana plugs from 2 sides. These are some 3D printed structures to hold them. And you see duct tapes, the famous duct tapes in labs. So you apply some positive potential on the banana plugs, and then you take a transformer and amplify or a variac, and you amplify the voltage coming out from your wall, right? So it's 60 hertz AC signal in North America, 50 hertz in India, and then you apply on diagonal blades, and then you can create this confining potential. And instead of atomic ions, what you can do, take fine powders, any powder, and then you rub it against a cloth or something, and it charges up, and you can drop them, and essentially that creates an ion trap. So it's very simple, and this is exactly what we have built, similar to 4-rod trap, but instead of rod we are using blades. This is just a demo. Let's see. You can see live. You can even see some extended orbits. You can even see some extended orbits of some of those ions there. So this is a fun experiment you can build. Now in the lab, of course, we want this to be slightly more sophisticated to work with neutral atoms, work with atoms, atomic ions. So what you do is we have, again, this 4-rod trap inside an ultra high vacuum chamber, and you need to bring in all the electrical connections. So these are the 4 rods, and typical dimensions are 500 microns between those rods. So this is still a pretty big as far as ion traps are concerned. The same ion trap from the side window, and you can see the 2 needles here. The ion will be near the center roughly. This is a macroscopic trap. Nowadays you can get much fancier traps with microfabrication where you have hundreds of electrodes. So we are also using this particular trap built by the Sandia National Laboratory in the US for another experiment that we are building. And then the whole thing has to be evacuated to ultra high vacuum. So there's a lot of science and art on vacuum technology. How do you get to low vacuums? You need vacuum pumps and pressure gauges and everything. And then once you have the chamber ready, you put on magnetic field coils for creating quantization axis, controlling Zeeman shifts and all inside your atom. And then you put a microscope objective, and then take that light, bend it, and put it on a camera or a photomultiplier tube, which you cannot see, it's behind this black box there. And then you can see those atoms because now you have a microscope objective. So inside the vacuum, what we have is an atomic oven. It's essentially a small needle, right? Inside the small needle, like a couple of millimeters in diameter, you put some material that you want to trap. In our case, it's Ytterbium. And then you send some current. You see this copper wire here. You send a few amperes of current that heats up, Joule heating of the tube, stainless steel tube. And because the pressure is so low, lower than the vapor pressure of that solid to liquid transition for that material, what happens is the atom comes out just in no liquid form, just spits, sublimates. And then some of those atoms, the oven is oriented in such a way that some of those atoms are now flowing through the trapped region. They're still neutral atoms, so they don't see my trapping potential yet. But then we can send laser beams and photoionize them. Right here, the laser beam is pointed at the trap center. And we send another laser beam that cools using all these, beautiful laser cooling techniques. So the result is that some of those atoms will be ionized and they will be so cold that now they are trapped inside the confining potential, the ion trapping potential. And as you keep your ionization beam on your camera, you will see 1, 2, 3, 4 individual atoms popping up. And whenever you are done with however many number of atoms you want to work with, you just stop, shut off the ionization beam, shut off the oven, then there are no more atoms. And those ions stay for a really long time. For example, a single ion in our trap stays for 3-4 months often. And my students have recently started to name the atoms if they like a particular ion, and that has helped them in doing some science because they stay there for such a long time. What's also interesting is these pictures that you are seeing of real single atoms. This was taken by a very simple camera, and we can do that because ions are so cold, they don't move, right? And they scatter photons again and again, and you can image them on a simple camera here. Sometimes if the wavelength of emission is in green, you could even see with your naked eye. Unfortunately, Ytterbium is not green fluorescing, it's in UV, but our eye is not sensitive. But barium, for example, in principle, if you turn off all your room lights off and you can stare, you can see a single atom with your naked eye. And then, this is the lab. There are lots of lasers to make sure everything is enclosed properly, but you may have seen other optics labs very similar. So let me pause here for see if there are questions on how we trap atoms. Anything?
Isabel, I have a small question.
Sure.
So when you said that you can trap the atom for months, in the background, the radio frequency is always there, and the atom is actually dancing. It's undergoing some stochastic dancing. Is that correct?
That is exactly correct, and that is one of the things that you want to minimize, right? So, right. So that is why you want to. So once you trap an ion, if you don't do anything, meaning if you don't have fine control over the position of those ions, you're absolutely right. This what you call micromotion, so stochastic dancing, it tends to heat up the ion system, and eventually it will be hard to cool those ions. And that's problematic, right? So what we do is we apply small voltages on those rods in addition to the radio frequency to fine tune the position of the ions to exactly position them at that RF null line that I was talking about, which is the symmetry axis on the trap, on which the amplitude of that RF is 0 or nearly 0. So the ion still sees the confining potential, the time average, but it doesn't actually dance, or it still dances. I think there is a unavoidable part of micromotion, but which is minimal, much lower than basically the heating rate here.
But it's a classical dance, so it doesn't affect the quantum thing that you are looking at.
So that is a very nuanced question. So in general, you are right. It's a classical dance. However, these ions, these are in a bunch of Coulomb particles, so they have vibrational modes, and those modes have very different frequency than this frequency of this RF dance. However, there is always going to be a little non-zero coupling between any mode and this frequency, right? Because a mode is never perfect harmonic. And this is a system where you are constantly pushing energy through this radio frequency into the system. So however little your coupling is, it will affect those motional modes. And as I will show, those motional modes are essentially what we use for doing quantum gates. So after you include all of these, indeed micromotion could be a problem for quantum operations, but there is a time scale which is coming from, how long does the micromotion take to affect those motional modes through the harmonicity of the modes themselves. And
So
there is
it's a source of incoherence.
Exactly.
Incoherence. Okay.
Exactly.
Thank you.
So that's also something fighting. Yeah. So there's a lot of layers of classical physics and quantum physics that come into these systems. Yeah. Thanks for this question.
So if you go to the Rajibul, if you go to the last element of the rare earth ion series, I mean the element next to ytterbium, lutetium, which is much smaller. So does it work? The same thing works?
So I believe people have been looking at lutetium. I don't know of any group that uses lutetium. So ytterbium has some beautiful properties. It has a filled F shell, and it has I believe also a filled D shell, although it has some D excitation too that you can get. So despite its complexity and despite being a rare earth element, surprisingly, if you look at the basic structure of ytterbium, it's very much like a hydrogen atom. So it has a hyperfine state where the hyperfine states are separated by about 12 gigahertz, which is a number that one can work with. You can get sources and amplifiers, not too complicated. And then its transition to the P state, S to P state, that's the transition that we use for laser cooling, is at 370 nanometers, which is also a wavelength it's UV, but not very UV. So you can get readily available diode sources, laser sources for that transition. So there are many other properties for ytterbium. Yeah. Okay, let me speed up a little bit. So actually, one of those properties here is that the ions, because the hyperfine states of ytterbium, it's very hard to affect hyperfine states, right? Because hyperfine state is not just electronic, you have the nuclear wave function. And in particular, you can choose two hyperfine states that have zero Zeeman state, zero magnetic projection quantum number. And those are the so-called clock states. And these states have very long coherence time. So this recent experiment from Tsinghua University showed that you can take a single qubit, and between these two hyperfine states, you can have a quantum coherence exceeding 1 hour, right? I mean, think about that. You have single ion, you can create a quantum superposition, and then you go out, do your groceries, come back, and the quantum superposition is still there. So that's quite beautiful. You can use a lot of atomic physics tools that have been developed over last many decades, a lot of them for atomic clocks, for near perfect state initialization and detection. These are standard AMO techniques, atomic molecular and optical physics techniques. For example, optical pumping, spin-dependent fluorescence. So in groups, people have shown really impressive state preparation fidelity with an error that is now 10⁻⁴ level error. Similarly, you can entangle, I'll say a little bit more about that, interaction between spins with an fidelity that has several nines, and we keep adding these nines. So right now it's 99.9% fidelity, and it's getting better. So how do you do coherent manipulation of spins? As I mentioned, there are two hyperfine states separated by about 12.6 gigahertz here. So you can either get a microwave source at 12.6 gigahertz and then broadcast the microwave source, and your atom will absorb and go between these two states. But for reasons that will be clear in a few slides, what we do is we take we take one laser beam, we take two laser beams and we counter propagate them, and we can control the frequency difference or the beat note frequency between those laser beams. And if you choose the frequency to be, the bit node frequency to be the hyperfine transition frequency, then effectively you can create a lambda system with the p half state as the virtual excited state, essentially, to transfer population from spin down to spin up. Right? So if you keep that light on, let's say you initialize in spin down state, and you are in this y-axis of this plot, you are looking at the probability of excitation to spin 1, and you keep this light on, as a function of time, the system undergoes two-level oscillations. So this is the Rabi flopping, two-level Rabi flopping. And the systems are so clean, the lasers are now, so little noise and your qubit is so good that this two-level Rabi oscillation can go on and on for, hundreds and hundreds of flops. So if you are speaking the language of quantum simulation, this particular data was taken in Maryland. It's an old slide, but pretty much every ion trapping lab has similar Rabi flopping data. So if you take, if you're speaking the language of quantum simulation, essentially what you are doing is by turning on this light, your block vector is precessing on the block sphere, right? So this is equivalent to bringing in a magnetic field onto your spin system. So this two-level Rabi flopping essentially simulates a magnetic field for us. And it couples to the spin component along a direction phi, and phi could be a combination of Sx and Sy on the equatorial block plane. And we can choose that angle phi by choosing the phase of this bit node, which is chosen, which can be chosen by acoustic modulators and devices that can control the phase of the optical field. So this is how you simulate a magnetic field. And if you want to create a larger magnetic field, effective magnetic field, all you do is simply increase the intensity of your laser beam. If you want to switch off the magnetic field, shut your laser down, right? And you can switch light at a much faster time scale than a real magnetic field created by magnetic field coils. So this is one advantage of using simulated magnetic field using light, because you have full control over amplitude, how fast you can switch, and also the direction at which the magnetic field is pointing at.
Sorry, a short question, Isabel.
Yeah.
So this is Zeeman field, synthetic Zeeman field.
Yeah.
There are also discussions about synthetic gauge fields. That will be a separate story altogether.
That is correct. Yeah,
Okay.
It's just a Zeeman. Yeah, that's right. So now the hard part. Okay, so the previous example was just acting on single qubit, right? There was no talking about multiple qubits. But of course, the interesting part of the Hamiltonian many-body system is the many-body part. So you need to build up interaction between spins. So to build up the interaction, you're looking for some common bus that connects multiple ions. These are Coulomb particles, charged particles, and therefore they vibrate together, right? So there's a confining trap and there's Coulomb interaction, and then the competition between them. You have the equilibrium position of the ions, and then you perturb them a little bit from the equilibrium position, and they undergo vibration in different normal modes. And this is a collective normal mode, and therefore you can make use of that collective normal mode to mediate interaction. So how so? I take one example. Let's say I have two spins here and here that I want to connect. So let's say I bring in one laser beam and I tune the frequency of the bit node of that laser beam to be the spin flip frequency that I talked about in the previous slide, the hyperfine frequency, plus the frequency that it's needed to excite a normal mode of motion. Okay, so it's a slightly higher frequency. So now what I'm doing is that spin flopped and that spin flipped, and then you also have a little bit of motional mode. Okay, this is just for illustrative purposes. I'm showing the whole ion chain as vibrating, but in reality, it's essentially, you can think of like a Fock state, exciting a Fock state. So now the second spin, it has not flipped yet because it hasn't seen any light, but something is going on because it's vibrating. And this is the trick. So now you bring in a second laser beam, but you tune the frequency of your second laser beam such that it's the hyperfine splitting minus the motional mode frequency. So it has a little bit of lower energy than the motional mode. So if you turned on, if you bring in that laser beam, now this ion can flip at the expense of killing that phonon, right? If the phonon did not exist in the first place, then that laser will not do anything because it doesn't have enough energy to flip an ion. And I'm assuming that I'm starting with a state with 0 phonon, which we can create experimentally. So by this, if you wish, a virtual excitation and annihilation of this phonon, you effectively coupled these two spins. And this is what you use for entangling operation. You can write down the Hamiltonian for this operation, and turns out it's nothing but an Ising interaction. With the Ising coupling Jij, depending on a bunch of parameters I will show in the next slide, but depending on how fast you flip, what kind of phonon you are using for this interaction, and also you can complicate your control a little bit and get a flip-flop interaction, or also get an XXZ, Heisenberg interaction, various kinds of interaction. So these are your favorite spin models that theorists love. So this protocol, people have been proposing various kinds of protocols for creating ion entanglement. In 1995, Sirac and Zoller, that was the first protocol. And then most labs nowadays use the Mommer-Sorensen protocol in 1999. Okay, so a couple of words about the spin-spin interactions. So that the effective interaction between ions I and J, if you ask what should they depend on, without going into the detailed derivation, we can rationalize that they must depend on the laser intensity, like how fast I'm doing this single qubit flopping operation. So these are the Rabi frequencies, omegas. They should depend on some basic quantities like the mass of the ion and the momentum difference, which is how much momentum you're imparting, and then which mode you are using, because different normal modes take contributions from ions in a different way. For example, if you shine a big fat beam, so no individual localized beam, but just one big fat beam on all the ions, and then you tune the frequency, the beat note frequency, close to the collective center of mass mode where all the ions are moving together, then you can imagine all pairs of ions are undergoing the Ising interaction. And there is no concept of who is nearest neighbor and who is farthest neighbor, because in that mode, all the ions are equivalent. So in effect, when you convert that into the Ising interaction, effectively it's an infinite range interaction. You can go to the second mode, second transverse collective mode, where the mode looks like this. It's a tilt mode where the ions on the outermost ions, they take part more vigorously than the ions near the center. And when you convert that into spin language, it's actually the outermost ions, they interact with the strongest interaction. And the ions near the center, they almost don't interact. And further, the eigenvector component has a relative minus sign between outside and inside, between the two edges. And you can use that to control the sign of this interaction, Gij. So this is an example of creating a model which has relatively short-range ferromagnetic interaction with long-range anti-ferromagnetic interaction, and you can get domains and all such from such a system. And similarly, there are other modes with lots of interesting spin couplings. So all of these you can do without changing anything in your hardware except just a frequency knob, which is a very quiet knob, very controlled knob in the lab, and you immediately have access to lots of different kinds of spin Hamiltonians in the same physical system. So in general, you have these n vibrational modes for n ions in any dimension. And if you make your system slightly more complex, and instead of using one beat note frequency, let's say you are now driving all these motional modes carefully, so you are mixing the nature of various motional modes and also addressing individual spins, then in principle you can gain full control over this Ising coupling matrix. You have n choose 2 interaction, n square over 2 roughly, and then you have n frequency knobs and n position knobs to control your light. So you have n square now. So essentially it's a fully controlled system. Of course, experimentally controlling this is challenging, but in principle you have full control. And that leads to some wonderful feature of this trapped ion system that I was mentioning earlier to Professor Bhaskaran's question, that even though it's a one-dimensional system, but you can in principle tune these bonds in such a way that they look like a programmable interaction graph. The programmable interaction graph looks like, a 2D lattice or a Kagome lattice. And what's interesting is you can even change them on the fly within the same simulation. You can go from one lattice type to another lattice type, because all of this is controlled by essentially controlling the laser light. So, okay, just as a slight detour here, I know I'm running out of time. When we are thinking about this full control of the Ising Hamiltonian, we realize that the control itself is not a quantum problem, but the control itself is hard. Namely, if you want a target lattice, right? So let's say a theorist tells me, I want this very strange lattice. I want to work on that. Tune your system. So then I still need to find out how to tune my individual laser, the Rabi frequencies, the frequency and the intensity. So this direction is easy. If I know what my Rabi frequencies of each ion are, then it's very easy to compute the Ising coupling. There's an equation for it. But if you tell me this is the Ising coupling, find out how should I tune my Rabi frequencies, that is a hard problem. And turns out this is one of those examples where machine learning was of great help, because what we could do is we could synthesize data with various different Rabi frequency patterns, right? And then we train a neural network and we get what kind of Ising couplings we get. And if the neural network is fully trained, now you feed into that neural network, the the coupling matrix on demand that your theorist friend wants you to make. And then if the network is fully trained, then it should just spit out a bunch of Rabi frequencies, which you can then program your lasers on. And we tested those. And it turns out that indeed, with less than 1% error of interaction matrix, you can create arbitrary lattice geometries if you have programmable control over your laser. So you can create a 2D triangular lattice, a cubic lattice. Of course, you are wrapping a 1D into 3D, so you need more ions. Just one cell will require 8 ions. There's that disadvantage compared to actually trapping a 3D system, but you can still do all of this. Okay, so if there is a quick question on this.
So, Rajibul, this itself is like a complexity problem, the inverse problem.
It is.
So you use machine learning. Fascinating, I see.
Yeah, so I didn't know machine learning before, but this was an example where it actually works. And what's nice about this problem is it's verifiable. So machine learning gives you some answer, but to verify that is very easy. It's just that equation. So you know that your answer is correct. The complexity comes in this problem in the form of how long it would take to train a network. So there is a certain memory requirement. We can talk about it later, but that's where the complexity comes. But we tried with up to 50 ions with arbitrary geometry, and the machine always gives a solution that looks reasonable experimentally within this few % error.
Fascinating. Thank you.
Yeah. All right. So it's already an hour. We have been having discussion. How long can I get extra, Professor Rao?
Yeah, how much more time you need, Rajiv? You can go on. It's very interesting.
Okay. 10-15 minutes since we are having a discussion together. Yeah. Oh, yes, please go ahead. One of the questions. Yeah.
So how did you train the algorithm? Like, since, this is already quite complex and you need to have some practice stuff, right? I'm also not an expert, but this is this is what struck me the moment you said that.
So this work, I by no means I'm an expert on machine learning. This I worked with my colleague Roger Melko, who runs this Perimeter Institute Quantum Intelligence Lab for using machine learning techniques for physics. So we tried various machine learning algorithms, and turns out that a very simple neural network, a feed-forward neural network with a very simple cost function, was enough to train this neural network. And there's a reason for it. And the reason is we are not interested so much in the exact value of each coupling. So if you look at this formula, Jij, so you have your Rabi frequencies, and then you have all these contribute. So sorry, I didn't explain all of that. That will go into too much detail. But these are basically the normal modes, right? So the frequencies and the eigenvectors and all of those, and then you have the Rabi frequencies. What we are interested in here is the shape of the coupling, not
so
so
you're
much.
interested in the connectivity.
Exactly. The shape, the connectivity of the coupling, and not so much about the exact magnitude of each coupling, because that's something that we can scale by choosing our overall, a constant multiplicative factor on our laser parameters, on our laser intensity, global parameter on our laser intensity, right? And that essentially simplifies the problem enormously. So my student actually tried solving the harder problem first, where I told him, give me a 1 kilohertz coupling on that particular bond, and 1.5 kilohertz on that particular bond, and it never worked because it's too fine-tuned for the neural network. But the moment we normalized everything and only training for the shape or the connectivity, as Professor Bhaskaran puts it, then it becomes fairly simple. So these are some of the parameters, and you can look up this the paper, Quantum Science and Technology, to do this. Yeah. Does that answer your question?
Yeah, sure. It's fascinating.
Thank you. All right, so now let me switch gear and let me talk a little bit about some optical engineering. I hope there are you have lots of experimentalists in the audience. So hopefully I convinced you that if I have a lot of control over individual ions, the optical control, then these quantum simulators could be very powerful. But experimentally, of course, getting those control is the challenge. And as hardware engineer, we work on various ways to shape our laser beam so that you can then talk to individual ions. So let's consider a very simple problem, or simply stated problem. It's actually a pretty hard problem, which is how do you talk to a single ion in this chain? In a classical processor, you want to talk to a single memory cell. Well, you just send, there are current lines, there are connections to each memory cell, and then you type the correct word, sends the correct current to that particular cell and activates that. That's a classical processor. In our quantum processor or simulator, if you want to talk to just one qubit, then you need to send laser beam to that one qubit. The challenge here is to do that without affecting the others, right? There is an additional complication that in most ion traps, especially these macroscopic ones, the ions are non-uniformly spaced. So you can see near the outside, this ion sees too much Coulomb repulsion from all the ions to the left, right? Compared to the ion at the center, the Coulomb kind of cancels from left and right. So these ions are pushed a little bit outwards. And as a result, some of the more readily available commercial technology, like using a multi-core fiber switch and all, becomes quite complicated. But there is a more fundamental problem which anybody working with optics has seen, and this has to do with the aberration. So consider this chain of ions, and what I'm doing is you have these ions in a bunch of ions in this trap, and outside you have a microscope objective, and then you focus the light on the camera. Now, if you take a picture, you would often see that each ion doesn't look like a beautiful blob of light limited by the diffraction, but they have lots of tail. And those are signatures of optical aberrations. So if you use the same microscope objective to send light back onto the ion, it also has the aberration. And what that means is if you want to, let's say, send your light to this particular ion, so the green dashed light is the ideal focused beam where the intensity has dropped to very low values at the neighboring ion. This is what you want, but because of aberrations, what you get if you measure the intensity with the ion, for example, by monitoring the Doppler cooling signal, laser cooling signal, then you see something like this, the blue curve. So this is an actual measured signal with our ion. So this little displacement you can fix by tweaking the mirrors and all, but then you see what the ion sees is a considerably broader aberrated beam which could have weird features, and you are losing a lot of intensity, peak intensity, because the light is aberrated. And anybody who has worked with optics knows about aberrations, right? This kills us. So how do you actually fix this problem? And you have seen aberrations in many different contexts, right? You have aberrations called astigmatism and coma and cylinder, basically, which is astigmatism. You know, some of us, we need to wear cylindrical lenses. So because we have astigmatism, these are all aberrations, wavefront aberrations. So if you want to gain full control over these ions, you need to create a programmable aberration corrected optical system. And how do you do that? So in our system, the way we do that is by introducing a hologram, a programmable hologram. A hologram is a device which you can use to program the wavefront of light, both amplitude and phase, such that if you know how much aberration you have in your system, and I'll tell you how we know that, you can compensate for it by programming negative of that aberration in the wavefront itself and pre-distorting the wavefronts such that when the light goes through all the optics elements onto the ion, it's nearly perfect, what you want. So what do we use for programmable hologram? We use a digital micrometer device. These are essentially projectors that are becoming very mature nowadays. You see them on movie projections, on in your seminar room, the projector you have, there is a device like that. So inside there are tiny MEMS mirrors, about 10 microns big, and the one that we have has about 2 million mirrors packed on a small chip, like an inch scale chip. And each mirror can be tilted on and off. So basically 2 directions, you can call one on, the other direction off, and you take light along one direction only. So you can effectively create a grating on this hologram, and you can play with the local intensity and local phase of light by playing with those grating lights, and you can full control over the wavefront. Of course, the question is, how do you know how much aberration you have in the system? And in our system, we use the ion itself as an aberration sensor. How do you do it? So you have your hologram, which is placed in a Fourier plane, meaning a focal length away from your objective lens. Ion is the focal length away in the other direction. So first you do is turn on small 2 patches, and the light coming from those interfere on the ion and create this standing wave, right? And you can scan those standing wave in space by controlling the phase of a small patch on your Fourier plane, and then you can use the ion to measure that intensity. So this is a signal as measured by ion itself, the fluorescence light from ion. And as I play with the phase, I see that the interference fringes move. So by fitting those, I can find out what's the relative phase between a reference patch and that patch. And then I can move to another point in the Fourier plane, and I can take another interference fringe. And if the phase on the Fourier plane is perfectly flat, the optical phase, then the interference fringe should be independent of the orientation or the exact location of the second patch, as long as they're same spaced and all. So the message here is, by controlling the this reference, the second patch with respect to the first patch, we can map out the optical phase in the entire Fourier plane, and then you get something like a phase map, right? So, and if you do that with ion, you will see roughly in about a wavelength, this is 370 nanometer, about a wavelength of optical aberrations in the Fourier plane. And then what you do is you dial in that phase, negative of that, onto your hologram. So you pre-distort the beam with negative of that aberration, and that should ideally make a perfect spot size. Does it? It does, almost. So now after we have corrected for that, the same beam which was previously blue now looks like orange. And the green dashed again is the perfect diffraction limited spot that you get from textbook, right? So the orange beam is almost perfect. And you can calculate how much aberration you have after compensating for it. And now it has gone down to basically, if you look, most of these spaces is like lambda over 10. For comparison, lambda over 10 is the aberration, lambda over 10, lambda over 20 is the aberration that you get from a single optics, right? If you place it properly. We are talking about the total aberration in a beam path, which is over a meter long. It has dozens of optical elements and a microscope objective. And we can compensate for the aberration of the entire system to better than lambda by 10 and get essentially perfect situation. So you can read about it in this publication, recent publication.
Sorry, the width of the yellow peak is a region where the single ion is running around.
Yeah, that's right.
It's not the size of the atom. It's much bigger.
That is correct. It's much bigger. We are limited by the diffraction size.
Yeah.
So the trick here is we want to make sure that by the time you go to the second ion, which is a few microns away, this intensity has fallen down to a very low level.
Thank you.
Yes, so using this method, using gaining full control over the aberrations, we can control the leakage light to the neighboring ion to 10 to the minus 4 level. So this is experimentally observed. Well, normally it's hard to get even up sub percentage level. And remember, your next ion is only up 3-4 microns away. All right. So as an outlook, you can use these holograms for doing more complex things, which we are doing now. For example, if you want to address multiple ions without affecting their neighbors, because you want to create these controllable quantum gates or quantum operations between target ions, now you can do that. And note that I make no assumption about whether the ions are equally spaced or not, because everything is programmable. So what you do is you program your hologram, and again, how do you program the hologram efficiently is another control problem. And we report an iterative Fourier transformation algorithm in this publication that can give you very high quality target intensity profiles. But then you can create intensity profile like that, right? So essentially what you're doing, let's say consider, these are just separate pictures. So what I'm doing is I'm taking one big fat laser beam reflecting off that programmable hologram, and by the time that light goes to the ion, its intensity looks like this, the entire patch. It's 0 pretty much everywhere. 0 means very low value, and then it's your target intensity at your target ion number 1, 0 again, and then target number 2. And you see the background that you can create is lower than 10 to the minus 4, which is kind of the state of the art actually. So this is already state of the art in how well you can address individual ions. And this scales to over 100 ion because of this programmable nature. So we're going to employ all of these in doing some simulations in the hopefully next couple of years. And another, as an outlook, condensed matter physicists in the audience probably will like this, that now that you have such exquisite control over light going to individual qubits, you can think about partial measurements. So partial measurement means you are measuring part of your many-body system without affecting, unless there is a basic level of disturbance that is always present. You have entanglement, but other than the fundamental limit, without affecting any other qubits. And more recently, like very recently, last few years, there has been tremendous interest in the condensed matter community in these partial measurements, because it turns out that if you mix coherent evolution with these partial measurements, there's a competition between them that can lead to various kinds of many-body state with different entanglement between them. And in particular, there is a possibility of a phase transition that's driven by this ratio of how often you measure how many qubits versus the coherent spin evolution. They compete with each other. So together with Roger Melko's group, we put out a proposal very recently that we are going to try in our experiment. There are already some very preliminary experiments coming out from other research groups. This is from Chris Monroe's group at Duke, Maryland at Duke, and this one is one of the original papers coming from Matthew Fisher's group talking about this measurement-driven phase transitions. So with that, let me pause this section, and I think this is my last section, unless there are questions on this holographic addressing?
Just a technical maybe question.
Yeah, please.
Have SLMs, right, which could also help you correct the wavefront in some sense. So did you prefer the DMDs for some reason?
Speed.
Speed.
So yeah, so DMDs, because these are MEMS mirrors, they can be switched. The mirrors themselves can be switched in a few microseconds. But then right now you're limited by essentially the data transfer rate through the FPGA. But even if you include all of this, that you can switch between DMD frames at, I'd say realistically at 20 kilohertz. So that's 50 microseconds, right? And these quantum operations themselves are of the order of that, microseconds to 100 microseconds kind of time scale. On the other hand, if you use an LCD based SLM, and the best one even we got is much slower than that. And the second reason is we unfortunately have to use ultraviolet light because Ytterbium, that's the wavelength 370. And again, the reflective mirrors have a better, high damage threshold, so low damage probability than many SLMs, many LCD-based SLMs. So these are two reasons. But yeah, you can also use an SLM for this.
Yeah.
Yeah. All right. So unless there are other questions, let me give a couple of final thoughts on these. And this is again, as an experimentalist, we talked about quantum supremacy, quantum complexity, but there is another complexity which we experimentalists face, which is the hardware complexity. See, when I started my PhD in 2007, trapping an ion and doing basic simulation with 2 ions, 3 ions, that would give you a fancy paper because that's pretty new. Now the field has progressed to the point that you have to include all of this individual addressing and very high quality of simulation, long coherence length, everything in order to make progress in this field. So the hardware in a lab gets more and more complicated. Right? This picture in the background, the typical optics lab that you will see, we have, perhaps hundreds of mirrors and lenses and other optics and optomechanical elements on the table. We mount those, use mirror mounts, use pedestals, and then clamp or fork to clamp them down to our optics breadboards. And so in effect, we are creating too many moving parts in our labs, right? Your temperature in the lab changes by a couple of degrees Celsius, and then all of those moving parts move a little bit, and then there are vibrations. And constantly, it's an experience, and anybody working in an optics lab, you constantly have to tweak things. Right? So a typical daily routine is a grad student shows up in the lab and spends first few hours tweaking up all the fiber couplings, all the lasers, everything. And it takes several hours a day just to tweak your system so that you can even start your experiment. And it's slowly becoming completely unmanageable. The hardware is becoming so complex. So last couple of slides, I'll show you some pictures here to show that how we can perhaps mitigate some of these issues. And a few groups that are building new labs are already adapting to this. So look at this picture now, and then see if we can go to something more better engineered. So if you know where your mirrors should be, you don't need all that flexibility of a post and a clamp because you are not moving it. You are fixing them to a table and then you are never touching it, except one is drifting. So the one approach would be making use of all these wonderful custom CNC milling capabilities that you can get from machine shops now. You can directly attach your mirror mounts to base plate. So first you draw a circuit, and then like on a piece of paper, and then convert that into a proper 3D CAD, and you mill out the base board with the exact slots and orientations for each of those mirrors. So these mirrors have dowel pins underneath. Probably experimentalists will appreciate that. And so effectively now you can create these circuits that, sometimes even walls are climbing in a vertical direction. And there are very few moving parts. They're all attached together. These systems are very stable. To give you an example, fiber coupling on a laser that we have done in our lab, this way, we didn't have to tweak that laser for basically 1.5 to 2 years at all. Like no fiber coupling didn't change. So that's it. And the very final slide is even the applications of quantum simulations are becoming too versatile now. Hardware is becoming challenging. So it's perhaps also time to think about beyond a single PI lab, for example, build quantum facilities where theorists with ideas can actually operate their ideas directly without having to interface with, with our graduate students. We have to understand what is it that you are trying to do and program onto their machine. So we need quantum facilities, and towards that goal, together with my colleague Crystal Senko, we have been building another machine that's very much work in progress. It will take several years to make progress on that, more progress on that. It's called Quantum Ion. It's essentially an open access quantum computer, and the long-term hope there is the system is built in such a robust way, engineered in such a robust way, with electronic control at all level, such that a theorist can tap onto, let's say, the top circuit layer if you want to give just a quantum circuit, or you can tap onto, let's say, just a native gate layer if you want to study more about, trapped ion gates, or something even lower that experimentalists might be interested in, how to turn on your laser beam to get the highest quality Rabi flopping, let's say. And yeah, so with that, let me thank you for giving me the opportunity and for your interactions, and I'm happy to take questions.
So, hi, Rajibul. So your last slide is threatening, actually, because experimentalists it's path to extinction of experimentalists in some sense, I suppose.
I don't think so.
But of course, it's really on a lighter note, but I just recall I had the opportunity to visit a submarine at some point. So in a submarine, there is a lot of automation, apparently even the U-boats had, but they needed to have 3 levels of rescue. When the first level fails, so I think experimentalists will still be required at least to rescue the theorist who has gone in and got trapped.
That's correct. And on a lighter note, as an experimentalist, you can always go to the lab and tweak a mirror now to kill everything.
Yes. But what about on-chip implementations of some of this technology? One keeps reading about it. The atom on chip. Could you comment on that?
Yeah, absolutely. Glad you asked. So this kind of engineering that's using the CNC mill robust engineering, I would say that it's still an intermediate which is available right now, which is what we are doing. But then indeed the future, if you ask me, I would say in the next 10 years, we would see a lot of what you can do on this bulk element can be integrated into a chip. Even you can think of a situation where the laser material with the tuning and a frequency tuning cavity, like a ring cavity, splitters, all the acousto-optic modulators, electro-optic modulators, they could all be actually created on a chip using some materials, aluminum nitride or whatever, some materials, right? And then sending light voltage. That would be wonderful. Indeed, some groups, notably MIT Lincoln Labs and more recently ETH Zurich, they have started putting various optical elements onto an ion trap itself. And that has tremendous advantages because now your whole system becomes monolithic, and you can put this whole thing inside a cryostat. So even though we don't need cryostat to cool the ions, that's laser cooling, but if you put the whole system into a cryostat, you win from much lower background pressure in the vacuum chamber, but also lower noise in electronics in general, right? But the challenge with this cryostat technology is that they vibrate. Even the best cryostats, they vibrate if you have a closed loop cryostat. So we're talking about ions, right? And we are talking about ions that are localized to submicrons. It's very hard to contain those vibrations. But now you can imagine if you combine the delivery optics and the collection optics on the same chip, the whole thing vibrates. So what, right? That doesn't do anything. So indeed, I'd say next 10 years, we're going to see a transition towards a lot of chip. I didn't have time to show this, but we have started working with, I think I just mentioned here, laser reach and waveguides. So instead of taking, free space splitting laser beams, but also, fiber splitting laser beam, what we did with a Stanford University in Australia, Macquarie University, what we did was we took a centimeter long glass, a few millimeter thick, and what they could do was they could etch basically a splitter from 1 to 17 channels using a femtosecond laser. So we couple some light. We could couple like a couple of watts of light. This is green light, 532 nanometer, for this quantum ion project, which is using barium ion. So longer wavelengths for that one, 532 nanometer, and you get reasonably equal branching ratio on all 17 channels. And this whole thing is this tiny. That's it. And then you temperature stabilize it, and no alignment necessary. There could be a global offset, but locally it's all fine. So yeah, you'll see a lot more than that. Yeah, that's great.
Yeah, the monolithic is really fascinating. In fact, femtosecond lasers themselves have started taking advantage of monolithic designs and have become much more technical. Maybe a very naive question at the end of your talk. So why would you have chosen ions as against neutral atoms? Like you're anyway sort of laser pulling them, or conversely, like what kind of scenarios would motivate using neutral ions, neutral atoms instead?
Yeah, as I mentioned in the beginning, neutral atoms would be great for certain kind of problems. Neutral atoms have the advantage of having the number. You can pack thousands of neutral atoms into a system, whereas with ions with this Coulomb, packing even 100 is a challenging, because they can be very close to each other. So neutral atom would have advantage, but ions have the distinct advantage of being able to do very high quality quantum gates. Some neutral atom researchers are now coming up with protocols which you can get high quality quantum gates between neutral atoms, but that is still not as matured as ion. I think part of the reason, the fundamental physics reason here, is that ion traps are much deeper because you have the charge degree of freedom. So you have access to much higher trapping frequencies. So take a system that's at millikelvin temperature, or let's say 100 microkelvin temperature. For neutral atom, that's a very high temperature, because your trapping frequencies are so low. 100 microkelvin is really bad, right? So they go to nanokelvin, even like half a nanokelvin. Whereas for trapped ion, 100 microkelvin is great, because we can create trap frequencies that are much higher than that. So when you are talking in terms of the quantum of motion, which is what ultimately matters, right? Even neutron star at that 10,000 Kelvin is, or electrons at room temperature is colder than my coldest neutral atom experiment in the world, because the electron's Fermi energy is so much higher. So everything is with respect to some energy scale here. And for ions, the energy scale is the trapping frequency, which is the minimum energy required to create an excitation. So it's easier to work with ions, because you have the charge degree of freedom and you can use electronic, not light.
Okay. Yeah. This is probably the best answer I've heard on this question. Yeah. Thank you.
Yeah. I think there were a couple of questions in the chat box. I think I can ask Anshuman. You had a question, right? Anshuman, I remember seeing that. Can you just ask the question now? Or Abhijit, you're around? Abhijit also had a question.
Hello.
Abhijit?
I had a similar question to Anshuman. Can I ask it?
Please. Yeah.
Yeah. So what happens in Floquet-Hamiltonian engineering is, I've read papers in which people were able to engineer an effective many-body Hamiltonian in a system of ultrafold atoms by applying a pulse sequence which they repeated periodically. And in the case of trapped ions, as you mentioned, you are addressing a pair of ions individually to engineer an interaction between them. And you also talked about that you had to use machine learning to figure out what parameters to set to find the interactions. So do you think a Floquet-Hamiltonian engineering approach will work over here, or are there any advantages, disadvantages of that?
Yes, it would work. In fact, I didn't have time to talk about that, but if you remember in one of my slides, I briefly talked about this hybrid quantum simulation, which is, the idea there is it's not exactly Floquet, but in the same spirit. So the idea there is you take an analog system, and so like you fine tune your system, use machine learning or whatever, fine tune your system to the best experimental capability, and then you turn on some gates, some local quantum gates, and you kind of repeat this. So that you apply that periodically. That's where the similarity with Floquet system comes there. And you can show that with much less control than this fully fine-tuned control needed for creating a full connectivity, you can create lots of interesting geometries. For example, you can create a two-dimensional square lattice or a triangular lattice using that kind of Hamiltonian engineering method. So I didn't have time to discuss this, but indeed one can use those. Now, as you know, a challenge with those kind of Floquet systems is usually heating, because you are periodically driving a system. You have to be careful about choosing your driving frequency carefully so that doesn't overlap with your many body energy states and you start heating up the many body system. So those kind of concerns also exist here in the trapped ion system. But indeed, you can use Floquet engineering and all Hamiltonian engineering methods employed in neutral atoms and NMR community.
Thank you.
Any other question?
I have a very short question.
Yes.
How do you ensure enough vacuum? Because your 5 or 6 ions can be pushed out by some thermal, let's say, oxygen atom in the oxygen molecule in there. So what is the vacuum that is needed?
Yes, this is this is a challenge we deal with in designing these systems. So the way to ensure that vacuum is like a few things. Number one, first understanding what's limiting your vacuum. If you take a vacuum chamber such as this, room temperature vacuum chamber, what limits your vacuum ultimately is this glass to metal interface. In fact, helium from the atmosphere can permeate through the glass. And that happens at low 10 to the minus 13 millibar vacuum. So that is kind of your fundamental limit at room temperature. But then often the vacuum that you can create in labs are several orders of magnitude worse than that. And the reason is you are using stainless steel for vacuum chambers, although nowadays people use titanium. That's possibly slightly better. And at that low pressure, you can think of stainless steel like a sponge, which has hydrogen inside. And at low pressure, all those hydrogens start coming out, hydrogen molecules. And this is called outgassing. And even if your vacuum is perfectly clean inside your vacuum chamber, you have no fingerprints, no oil, nothing, you cleaned everything off, you have large pumps connected to it, it's that outgassing that limits that vacuum. So we used lots of techniques that were perfected and trial and error in the vacuum community over many decades to passivate the surface. So for example, I don't know if you can see here inside the vacuum chamber, you can see the shape. Sorry. So here inside the vacuum chamber, you can see it looks like orange, kind of slightly bluish or orangish. It's not the color of a stainless steel. So what you are seeing there is a passivated surface. What you do is we heat up different pieces that goes into vacuum chamber at high temperature, typically 400 degrees Celsius in a vacuum, like moderate vacuum, 10 to the minus 8 vacuum. And at that high temperature, low vacuum, we bring as much hydrogen out as possible from the material. And then you create a thin layer of oxide by controllably allowing some atmosphere to get into it and oxygen. And what that oxide does is create a very thin layer of the stainless steel has chromium and other elements in stainless steel, and you create a thin layer of oxide, and that oxide prevents further hydrogen from coming out.
So this passivation is an art.
Yeah, very much. In fact, I'll tell you, our first chamber, when we tried passivating, I think we got a little bit excited and cranked the temperature up a little bit. And then when the chamber came out, it looked blue. It's beautiful, but we are not sure what we are looking at, like what kind of oxide we are creating. And then what happens is if you don't make this oxide layer very thin and almost monoatomic, then the oxide layer starts cracking, and you can see that by different coloration. It's not a beautiful single layer of oxide, and those cracks are where hydrogen will come out. So it is very much an art. That's part one of this challenge. Second is increasing conductance. Like anytime, so your pump is here, the red thing is a pump, and you see this is so far from the vacuum chamber, and you have constraints, mechanical constraints that prevent what's the conductance of air going through the pump. So we are designing our next vacuum chamber where we have maximized that conductance, and we think that you should be able to go at least an order of magnitude lower pressure than this chamber. So this chamber right now is at around 3 10 to the minus 11 millibar, which is already ultra low vacuum. But I think we should go at least more than an order of magnitude by just optimizing conductance for the new chamber. Yeah, so this is part art, a lot of vacuum techniques, and a lot of empirical science.
Thank you, Rajibul, for a wonderful talk. Very
Thank you.
inspiring.